Okay, this video is about, well, discrete random variables. So we're going to talk you through the whys and wherefores of all this and end up with an exam question. So if this all works for you and you follow it right through to the end, then hopefully you should be in a position to actually do an exam question of some level at the end of it all. Okay, so. Well, first of all, I probably need to, if you haven't looked at random variables at all, it's worth just, looking at the definition where we have got some random occurrence, and as a result of it, we can we get a value, and that value is random. Then that is a random variable. So here we go. Random is a variable that takes different values with different probabilities. So any one random variable, the probability that the random variable is 2 could be zero point 0.3, and the probability that it's equal to 5 could be zero point 0.1, or so on. We'll look at some examples, so that'll become a bit clearer. And we're talking about discrete random variables. They can only take a certain number of values. Okay, now in another video, we're going to be talking about continuous random variables, which can take any, because it's a continuous variable, obviously. So the difference might be when we're looking at the tossing a fair coin twice and counting the number of heads, for instance. Then the number of heads could be 0, 1, or 2, so specific number. If we're looking at heights of students and we measure their height, then the height could basically be anything. If we go to enough decimal places, then it could be virtually anything. So that would be a continuous random variable. Anyway, we're just looking today at at discrete random variables. Here's another one: rolling a fair dice and recording the score. So the score on the dice could be 1, 2, 3, 4, 5, or 6. And each of those would have, if it's a fair dice, would have an equal probability. Okay, so let's have a think about what we mean by a probability distribution. A probability distribution is a table showing all possible values that the random variable can take with its probability. All right, so again, going back to the fair dice situation, then the random variable can take 6 different values, each with a probability of 1/6. And this is the notation that we tend to use. So we tend to use a large letter, typically a large X, for the random variable, and the X is a specific value. So what we're saying is with the probability that the random variable will take a specific value is this for 1, same for 2, and so on. So have a look at this example. A biased coin, for which the probability of heads is 3/4 and tails is 1/4, is tossed once, and the number of tails is counted. Write down the probability function of X. Okay, so when the coin lands on heads, we're going to denote that as a 0, and when it's on tails as a 1. Right. So the probability that the random variable is 0 is therefore 3/4. That's what that is. Heads 3/4, and the probability it's 1 is going to be 1/4. So if we just write out the probability function, we're basically listing out all the probabilities, all the values with their probabilities, and that's exactly what we've got here. So this is simply the probability function for this random variable. We could put it on a graph, couldn't we? It would be a very simple graph in this situation. It would be 2 bars. One would be 1/4 high and the other one would be 3/4. Okay. So that's the probability function for one spin. But what about if we did it twice? then what's going to happen here? So the probability of two heads, right, we're going to use our sort of multiply rule. So this is going to be 9/16 head. A head tail, so the kind of the order sort of matters here is if we get a head with the first one and a tail with the second, then the probability of that is going to be 3/4 times a quarter. So that's going to be 3/16. The probability of tail and a head is going to be, well, it's going to be 1/4 times 3/4, actually the same number. But we've got two shots at getting a head and the tail, if you see what I mean. And then two tails is going to be a quarter times a quarter, so that's going to be 1/16. And we noticed when we add all these up, they come to 16/16. All right. Which is equal to 1, which is what we need our random variables to do. We need the probabilities of random variables to add up to 1. So now let's take a different look at it and say, right, okay, so now our random variable is the number of heads that we get. Now there are three values that this random variable can take. 0, 1, and 2. Okay, and we can actually kind of work these out from this calculation we've just done. So probability of no heads would be this last one, 1/16. Probability of one head, well, we've got that twice in the table, haven't we? So that's going to be 3/16 and 3/16. I'll just write that as 6/16. And then the probability there are two heads is the top one, which is 9/16. Okay. Right, again, we'll look at these 9, 6, 1, 16. So all that add up to 1. So this would be the probability distribution for the random variable that is the number of heads resulting from two spins of an unfair biased coin. All right, so that is that. Let's have a look down here. Probabilities of all the values that a discrete random variable can take add up to 1, as we've just said, and we tend to write it like this. So this is the sigma sign, which basically means we're adding across all the x's. So the probability that x equals particular value when we sum it across all x is equal to 1. So this is when we add up the probability that x is equal to 0, x is equal to 1, x is equal to 2. They all add up to 1. Right, the random variable x has probability function this. This is an example. Find the value of k. Right, the probability of a value, the random variable takes the value of x, is equal to k times x. Right, okay. So if we put these in a table, then what we've got is the probability of the random variable taking a value. 1 is k, 2 is 2k, 3 is 3k. What's k? Well, what we know is that these must add up to 1 then. 1. So k plus 2k plus 3k equals 1. Well, that's 6k equals 1, so k equals 1/6. All right. So this sort of question actually comes up quite a lot in your stats paper, or something similar to this. The number of hot beverages is another example, drunk by GP Pitt's tea staff each day. Yeah. Not PG tips, but GP Pitt's tea staff each day is modeled by the discrete random variable x, the number of hot beverages that they drink. All right. Okay, so this means that if we choose one person from the staff at random, then the probability that they drink a certain number of teas is given by this table. So at random, we choose somebody, the probability that they don't drink any tea is 0.1, and that they drink 3 is 0.2, and so on. 4 or more is A, if you're going to work out. Yeah, so A, find for part A, find the value of A. Well, again, we know that all these must add up to 1. So once we've taken out these first 4 rows, then basically A has got to be 0.2. Now, another thing we're going to be concerned with these finding these probabilities is the finding probabilities in a range, not just specific values, but in a range of values. So here we're we're looking at this table now that we know this last value to be 0.2. Find the probability that the random variable is greater than or equal to 2 and less than 4. So there we go. So that's another way of saying that the probability is 2 or 4. The probability of 2 is 0.3. The probability of 4 is 0.2 that we've just worked out. So we add those two together. These are mutually exclusive, so we can add them up. And that gives us 0.5. So that would be the probability that the random variable is greater than or equal to 2 or less than 4. Scroll down a bit, find the mode. The highest probability in the table is 0.3 when x equals 2. So the mode is equal to 2. Right. The question here, I've kind of added this in because what is also of use and of interest in these things is finding the median. Now, at this point, you have to kind of start remembering back to when we did graphs of data. We've gathered some data. We've sampled the speeds of cars and you know that sort of thing. You can start to see the similarity here. So when we're looking for the median, we're not so much looking for the middle value, but we're looking for the value such that the probability of less than that value is 0.5, and obviously therefore the probability that greater than the value is 0.5 as well. Right, so so we can see from the table then that the median is going to be somewhere in there. It's we'll not work out the value, but basically it's going to be something like um, it's in the band of 2 because everything less than up there is going to be 0.5 and everything down here is going to be 0.5. So we haven't got an exact value for it here, but we could work that out. Right, okay. So an unbiased six-sided dice has faces marked 1, 1, 1, 2, 2, 3. The dice is rolled twice. X is a random variable, the sum of the two scores on the dice. Find the probability distribution of X. Make that a little bit bigger. So if we produce this table, and for all those scores and all those scores, we can find the sum. So this table represents the sum. So that identifies all the possible values. So it's an unbiased dice. So all these values in here have got the same probability, and there's 36 of them. So each one has got the 36 probability of a 36. But however, we do have, well, look at 2, for instance. We've got pointer working. 2, 3, 4, 5, 6, 7, 8, 9. 9 different ways of um, getting a total of 2. Right. So that would be therefore 9/36. Probability of getting a 2 would be 9/36. Probability of getting a 5. Well, how many 5s we've got? 1, 2, 3, 4. 4 5s. So that would be 4/36. There. Okay, so that's the kind of the idea with that. All right. Right. Discrete uniform distribution. Sometimes you'll have a random variable where every value of x is equally likely. This is called the uniform distribution, e.g. rolling a unbiased dice. I'm just taking one value. We'll give you that, and we can draw a chart of that. There we go. So 6 bars, all the same height, and each height is 1/6, basically. A lottery involves a ball being picked at random from a box of 30 balls numbered from 11 to 40. The random variable represents the number on the first ball to be picked. Write down the probability function of x and find the probability that x is less than 20. Right, so the probability that the random variable will take any one particular value is 1/30. There are 30 balls. Okay, so each one is equally likely, and that is for x between 11 and 40. That's what the question says. The probability that x is less than 20 is going to be the sum of all these. Well, we start at 11 and we go up to 19, don't we? So that's nine different outcomes, each with probability 1/30th. So that's probability is going to be 9/30 or 3/10. All right, so that is that one. Okay, find the probability functions in A to C. Below, find K and write down the probability distribution of X. Well, I've kind of just done the first one, really. Probability that of X equals KX squared. So this is a probability um, distribution where, well, let's write it out. This is the way to do it. So when X equals 1, that gives us K. When X equals 2, we've got 4K. That's the rule, isn't it? K times X squared. And when K is equal to, when X is equal to 3, then the probability is equal to 9K. All right. So in other words, all these total these total up to 14K. So K is going to equal 1/14th. All right. I'll just have a look at B is going to be similar, isn't it? But let's just have a look at, at C. Um, and so in this case, we've got eight eight different values. So let's just draw a similar kind of thing. I have to freehand. Bad. X and the probability that X equals X. So we've got values 1, 2, 3, so 3, 4, 5, 6, 7, and 8. And so it's going to be KX for 1, 2, 3, 4. It's going to be K, 2K, 3K, and 4K, just like before. And this time for 5, 6, 7, and 5, 6, and 7. Oh, we haven't got an 8, have we? Get rid of that. Then it's going to be this. So it's going to be K times, for 5, it's going to be K times 8 minus 5. It'll be 3K. And then it's going to be 2K and K. So there's an interesting one. So it basically rises up, doesn't it, to the maximum probability in the middle. So if we add all that up, we're going to get 10, 15, 16, 16K. So the total is 16K, which we know must be what equal to 1 for it to be a valid probability function. K equals 1/16th. Okay. And again, this sort of question is quite typical where we've got maybe two different rules mixed in there. Right. Okay. So now I mentioned before we're looking for the probability of a random variable being between two different values. We kind of also have the concept of the cumulative distribution function. Written large F gives a probability that X will be less than or equal to a particular value. like a running total of probabilities. Again, think back to your cumulative frequency chart that you did. So it's sort of a parallel kind of idea, really. Um, and and these are quite useful when if we obviously are in need of actually doing um, probabilities less than or equal to a particular value. All right, so okay, so that's what we've got there. Um, the cumulative distribution function gives a probability that x will be less than or equal to a particular value. It's like a running total of probabilities. That's exactly what it is. Okay. Okay, and so basically, if we want the probability that this is just notation, the probability that the random variable is less than or equal to a particular value, then we are summing all the values up to that particular value, x0, um, of the probabilities that the random variable takes that particular value. So summing all the x's up to the value that we're interested in. Simple as that. The table shows the probability distribution of the discrete random variable h. Draw a table to show the cumulative uh, distribution function. Well, you can see quite easily here. So 0, 0.1, 0.2, 0.3, 0.4, those are the values, and these are the probabilities. So if we want the cumulative probability, then obviously for 0.1, it's just going to be that. For anything less than or equal to 0.2, it's going to be the sum of these two up to and including 0.3 is these. And then finally, obviously, the whole lot is going to be probability 1. Right. Okay, so that is our cumulative distribution function, and we'll have a look at the calculator in a bit and to show how that's sort of implemented on our calculators. Um, the binomial coefficients. In how many orders can 4 different ornaments be arranged on a shelf? Yeah. So imagine placing the ornaments on the shelf at one at a time, all different colors here. These are the white ones are just locations that we haven't used yet. Um, we've got 4 choices for the first ornament. Yeah. So we're filling the first location. We've got 4 different places that we can put it. 3 choices for the second, 2 then for the third, and 1 for the last. So if we multiply those things together, then we're going to get 4 times 3 times 2 times 1 equals 4 factorial, and that's 24 different arrangements that we can have. Right, now imagine you have n objects, but x of these are identical to each other, and the other n minus x are also identical to each other. So there's only really 2 different types. Could be arranging red balls and blue balls, for instance. Um, so the number of different arrangements that we can have would basically be is given by this. This is the binomial coefficient. You might have come across this before. Let's just be clear what we mean by this. If, for instance, we've got 4 red balls, and we've got 3 blue balls, then how many different arrangements can we have? Now, the point is here is that we sort of know that these balls are different balls, but when we arrange them, they're just reds and blues. So to us, if they were arranged like red, red, blue, red, blue, blue, red. I mean, it doesn't really matter which is R1 and which is R2 and so on. Okay. We start off by imagining that we can arrange these seven different balls. Okay, there would be seven factorial different ways of doing that. However, um, we're not interested in what order the R's are. You know, is it R1, R2, R3, R4, or are these organized R3, R1, R4, R2? It's not going to actually matter to us. So we need to factor out that. How many different arrangements are there of the red balls? Well, there are 4 factorial. So we need to factor that out. And then we need to do that for the blues as well. And that would be, being 3 of them, there will be 3 factorial. So actually, the total number of arrangements is going to be 7 factorial divided by 4 factorial times 3 factorial. And which we can work out, can't we? So if we cancel, the 4 factorial will cancel, giving us 7 times 6 times 5 over 3 factorial. Well, 3 factorial is 6, isn't it? So we can basically just cancel that with that, and that's going to give us 35. So the 35 different arrangements. Right. Well, we need this. We're gonna need this when we start looking at the binomial distribution. Okay. So so here's some examples. How many ways are there to select 11 players from a squad of 16? Right. Again, so they're selected or not selected. So we've got kind of 2 groups. You know, the selected are the red balls and the non-selected are the blue balls. So we've got 16 players. So basically it's going to be this 16 factorial divided by 11 factorial times 5 factorial. We often use this notation. We also use the notation NCR, which in this case, of course, would be 16 choose 11. Similar, how many ways to pick 6 lottery numbers from 59, and we're not bothered about the order of them. 59C6, 59 choose 6, 59 factorial divided by 6 factorial times 53 factorial, which is a rather large number. Okay, so that is that. Now, not for here, but there are situations where we might be bothered about the order of the lottery numbers, in which case what we're going to be looking for is NPR, and this is actually going to be something like 59 simply divided by 53 factorial. So we're not factoring out the order of the lottery numbers because it may matter. Okay, so that's all part of probability and combinatorics, but we don't sort of need that anymore just at the moment. So for each word below, find the number of different orders in which the letters can be arranged. Well, we don't have to do all these really, but at C, tart. Okay, so we've got 2 T's in there. So simply, well, we've got, if it's T1 and T2, it would be 4 factorial, but we need to factor out. So it's that. So it's going to be equal to 4 times 3, which is equal to 12. Stressless. Let's have a look at stressless. So what have we got? We've got 1, 2, 3, 4, 5 S's. We've got 1 T. We've got 1 R. We've got 1, 2 E's. We've got 1 L. We've got 3, 4, 5, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. That's right. So All right, so if they were numbered, it would be 10 factorial, but we need to factor out the order that the S's are in, um, and the order that the E's are in. 2 factorial, just 2, obviously. So that's going to give us the total number of arrangements of the letters stressless. Okay. Right, so that is that. Let's have a look at this. Habiba wants to arrange a total of 15 milk bottles in a line. There are 7 identical bottles of one type and 4 identical bottles of a different type. The remaining milk bottles are all unique. Find the number of ways. All right, so there's 15 milk bottles in a line. So that's where we start off, a 15 factorial. 7 of identical of one type. So we need to factor that out. We need to factor out the order of the 4 identical bottles of a different type. Um, there are basically 4 other bottles. Right. Well, this is a bit like our NPR, so we're not really we're not factoring that out, are we? So this is basically going to be what we're looking for. It'll be quite a big number, I think this. Um, all right, now we can cancel the 7 factorial part of all that, all divided by 4 factorial. Well, whichever way you like, really. That'll cancel with that. That'll cancel with that. So that's going to be our number, yeah, which would be quite a big number. I'm not going to work it out. Incidentally, these binomial coefficients always work out to an integer. And I think that can be proved, but I'm not going to do that here. Right. Okay. So next, the binomial distribution. Let's think of this example. I roll a fair dice 4 times. Find the probability of getting a 5 or a 6 on 3 of those rolls. Okay. So now for the binomial distribution, the terminology is to think in terms of a success or a failure. It's binomial because there are basically 2 outcomes, a success or a failure. Um, right, so for any one dice here, if we to roll a 5 or a 6 is going to have a probability of 2/6. It's a fair dice, so 2/6 or 1/3, right? And therefore the probability of a failure is going to be 2/3. Right, okay. So what can we get? Well, when we think about the order in which we do these, we could have 3 successes and then a failure. That would give us a probability of 1/3 cubed. Yeah, we've got 3 S's. 1/3 times 1/3 times 1/3 times 2/3 for the failure. So we'll work that out. That's going to be 2/81. 2/81. Success, failure, success is going to be a third times a third times 2/3 times a third, which when we arrange is the same thing. So that's going to be 2/81 as well. And same again. And same again. Okay, so there are 4 different ways of getting the um, the 5 or 6 on 3 of the rolls. Okay, so we sort of got what we've got is we've got 2 different outcomes. We can have success and failure. So what we're actually doing here is um, we've got 4 of these. Why has that come about? Well, basically what we've got is 4 factorial divided by 3 factorial times 1 factorial if we like. Yeah, okay. So when we are looking at how many successes we get out of a total number of trials, use the word trials as well, it's the number of rolls. So here the number of trials would be 4, and we're looking for uh, 3 successes. Then we can see that actually we're going to get this combination of probabilities is going to occur on a number of occasions, and the number of occasions is going to be given by our binomial coefficient, which is this. Okay, so in a sense, what we need to do is just calculate this and multiply it by that. Right, hope that's clear. So here's a kind of little formula for this. So the probability of X successes in N trials is going to be N choose X, which of course is N factorial divided by X factorial times N minus X factorial, times the probability of success to the power of X and the probability of failure to the power of N minus X. That's exactly what we did in this example. Okay, so that is what we want to calculate. I mean, actually, the calculator does a pretty good job of doing it for us, which we'll see in a moment. A random variable follows a binomial distribution as long as these 5 conditions are satisfied. Yeah, to be honest, there's the 2 kind of crucial ones really are 3 and 4. Um, um, 5 isn't really a condition. 2 is just the definition that we're using. Success or failure. It's binomial because there's only 2 outcomes. So that's the definition. And there's a fixed number of trials. But it's important that all the trials are independent. Okay. And that the probability of success is the same in each trial. So that question does come up quite a bit. What are the conditions for using the binomial distribution in this particular situation? And those are the 2 that you really kind of need to sort of remember. Right, here we go. A sewing machine operator sews buttons onto jackets. The probability that a button sewed by this operator falls off before it leaves the factory is 0.001. Doesn't sound very much, does it? On one particular day, the sewing machine operator sews 650 buttons. X is the number of the buttons that fall off the jacket before it leaves the factory. Right, at this point, I'm going to have to switch my screen if I'm going to get my calculator up. So, right, I'll be back in a second. Right, okay, so here we go. Now I've got my changed my screen, so I've got my calculator up here. Right, so X is the number. So let's just have a look. So if we go into statistical distributions and we go for the binomial probability distribution, option 4, we're just going for a single. You can get a list of probabilities, but well, then let's do that. We can either go for one single one, which would be option 2, or we could go for a list. All right, so we're going to go for a list. And so we're actually looking for the values that this can take is obviously starts at 0. And I mean, it could go up to, in theory, up to 650. So this random variable could um, um, actually take 651 values, couldn't it? Now, the probability of all 650 buttons falling off is extremely small, as you can see from this probability here. So let's just have a look at the first few. So I'm going to do 0, 1, 2, 3, 4. Okay. Number on the left there is just a row number. Um, so, and we've got 650 trials. The probability is this number here, 1 times 10 to the power of minus 3. And when we hit equals, we get the table. Okay, so the probability that no buttons fall off is this value here. Let me just cut that out and then I can a bit bigger. Try that again. Um, right, probability of none is going to be 0.528 and so on down here. Um, so now this with this probability here is very small probability. Then this distribution is very much skewed towards the left. Um, you can also use a calculator actually. I've got there's a there's all sorts of applets and little calculators that you can find on the internet. This one's quite good. And it graphs that all out. And if we wanted to find the probability that X is equal to 1, which one button falls off, then we can tells us that. If we want to work out the probability that X is the random variable is less than or equal to 3, do that. And that's going to be rather high. So the chances are that there's going to be no more than 3 buttons fall off when we see that. So that's quite useful. Okay, so that is how we would use the calculator. We can also use the calculator, say for a single value. Let's just do that. Menu 7 for single variable. So if we're just looking at the probability, let's go for 2, shall we? That is 0.11. So that's what we've got on our table there. Okay. Now the other thing is if we want to do the cumulative, so the binomial CD, then if we're looking for the probability that it's less than or equal to 3, okay, same parameters there, 650 trials with a probability of 0.001, then that's the probability of less than or equal to 3. So that's how we can use the calculator. Depending on what we're doing, if you're working on your computer, and then you could always use one of these little applets. Quite useful. And of course, these will draw your probability for you. It's quite interesting actually looking at the different sort of um, values of the probability and also the different number of trials to see how these work. In fact, let's actually do that now. So let's just have here's 100 and say we've got a probability of take that out there, probability of 0.5 to start with. Right, okay, look at that. So unsurprisingly, this peaks in the middle. 100 trials, a probability of 0.5. This is symmetrical distribution. I sort of expect that really. What happens if we have a probability of 0.3? Let's go for some different numbers. Let's go for 20 and 0.2. Right, okay, so now this is kind of showing as a kind of leftward. It's kind of skewed to the left, isn't it? Whereas if it was 0.8, if I can get that typed in properly, it's skewed to the right. Yeah, so you kind of expect 16 again, 0.8 times 20, 16. That is your most likely um, um, value for your random variable. All right, so that's quite interesting to play with that. You notice actually that, if for a large number of trials, then even with a small probability, um, then actually it's not a very good example. Let's go back to 100. Um, then it's kind of looking fairly symmetrical, isn't it? So the symmetry thing, it's a kind of a bit dependent on the size of the number of trials and also the probability. So as the trials gets bigger and this one gets nearer and nearer to zero point 0.5, you're more likely to get a symmetrical distribution. Right, okay, so let's have a look at an exam question. Um, Plastic clothes pegs are made in various colors. Number of red pegs may be modeled by a binomial distribution with parameter p equal to zero point 0.2. The contents of packets of 50 pegs of mixed colors may be considered to be random samples. So your sample, your trial number of trials is 50 then. Determine that probability that a packet contains less than or equal to 15 red pegs. Right, out with the calculator. So we're going into here. So less than or equal to. So we are looking for the cumulative distribution. And we're just looking for one value there, which is a variable. So less than or equal to 15 um, out of 50 with a probability of zero point 0.2 is going to be this value. Right, 0.97. Exactly 10 red pegs. Right. Well, we can use the probability, the probability function to do this. Um, so we want exactly 10 red pegs. Same parameters. 0.14 to two decimal places. More than five, but fewer than 15 red pegs. Okay. Right. So basically, we want anything that goes from 6 up to 15, up to 14, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is going to be the probability that the random variable is less than or equal to 14 and greater than or equal to 6. Right, so how do we do that? Well, on our calculator, we basically what we have to do is we have to subtract one from the other. So we have to do probability that x is less than 14, and then take away the probability. Well, if x is going to so basically what we want to take away is 5 and less. So that's what we would have to do. So we have to do two calculations there. All right. Okay, I won't do that now. Bobby Sly, a Sly student, claims to have counted the number of red pegs in each of 100 packets from 50 pegs. From his results, the following values are calculated. Mean number of red pegs per packet equals 10.5. Variance of the number of number of red pegs per packet equals 20.41. Well, we can't do that. We haven't got enough. I haven't told you enough to do that. That one at the moment. But the mean number of red pegs per packet. Well, what did we get when we got? I have to do it again now. I can't remember. So we're saying that. the variable 2 um, equals 0.13. So probability of getting 10 is actually 0.13. Well, we don't know about the means yet, do we? So let's just come back to that. Let me tell you about the mean and variance. Okay, so for random variables, we have the concept of the mean and variables. Now, you know about the mean and variance of a set of numbers. Okay. Um, but a random variable, how does that work? Well, what we're doing when we're looking at what do we mean by the mean of a random variable? Yeah, okay, so it is some measure of the kind of where do we think it's going to be? And what we're actually calculating is we call it the expectation of x as well. And when we talk about random variables, we talk about the expectation. And what we do is we basically it's the weighted value for all the possible values of that random variable. Okay, so what we're going to do is across all the possible values, we're going to multiply the value by its probability. And when we add all those up, that basically is the expectation. I probably see from that it gives you sort of a weighted value, doesn't it, by probability. Right, okay, um so that's the expectation. Now, we need a bit of maths to actually show this, but in the case of the binomial, then that is actually n times p. Right. Um, so just a word about the variance first. We can also calculate the variance because the random variables could be spread out in the same way that our data could be spread out. So in order to do that, we actually need to calculate the second moment. So that is basically x squared times the probability of x. So it's the sort of expectation of x squared minus the square of the expectation. Like that. All right. We don't have any ends in here because that's already factored out by the fact that we're dealing with probabilities and not total values. Right. So that would be the variance. And in actual fact, that is we calculate that by that. And if we want the standard deviation, therefore we take the square root of that. So if the mean is n times p, just roll back to here. So we've got a parameter 0.2. We're taking 50 pegs. 50 times 0.2 is going to be 10. All right. So the theoretical mean is 10. Now he's calculated it from from having counted them. What we'd say is we in 50 pegs we would expect 10. He's found 10.5. So his sort of calculation based on an experiment is actually quite a good estimate. Yeah. Right. So that would be that. So NP, as we've said, is going to be equal to 50 times 0.2, which equals 10. And NP times that is going to be 50 times 0.2 times 0.8. And that is going to be 10 times 0.8. is going to be 8. So his variance looks a bit skew with, really. I think I mean, he's calculated it, so but it doesn't really support the theoretical value. I think that's all we can say. So just going back to this and going back to the buttons example. So here are the first four probabilities. Um, I mean, there are a lot of the probabilities down here, but if we calculate the mean just based on these first four, then um, 0.52188 times 0 plus 0.33956 times 1 times this times 2, 0.02385 times 3. Well, just those alone come to zero point 0.6. Okay. Um, I mean, we theoretically our number should be 0.65, shouldn't it? If we multiply n by p. Anyway, we've got that far just by adding the first three. The rest are pretty small, so I think we'd find that if we carried on summing these over the whole 651 different values, you know, we would definitely get to that value there. Right. Okay. So that has been a bit of a run through binomial. There's a lot more to know about discrete random variables and the binomial probability function. But if you can follow all that and understand all that, then you're in a sort of reasonably good place to actually do quite a lot of the exam questions on the binomial. So, okay, so we'll call it a day there, and thank you for watching.